Hi, and welcome to Module 6 in Lecture 2. Now we're going to start moving towards, as I said last time, concrete examples of hypothesis tests. And we're going to start when we have categorical dependent variables and categorical independent variables. And to do that, we're going to use tabular analysis or crosstabs. You might also often hear that phrase as well. And the chi-squared test. Okay, so we do this whenever we have two ordinal or categorical variables. So ordinal or nominal variables, in which for both the independent variables and the dependent variables. To do this, we study a crosstab, which means we make a table of the frequency of combinations of the various variables' possible values, and then we compare them. So crosstabs will get us an ability to assess if the values on the independent variable are correlated with the ones on the dependent variable. And therefore show us if there are significant differences between groups. Okay, so let's do an example and see how this all works. Is there a difference in how Republicans and Democrats voted in congressional elections? Our hypothesis, as usual, is there is a difference. And the null, of course, is there's no difference. Okay, so what we do here is we have our table, hence all the tabular analysis, and we put all the frequency of combinations of categories for the independent and dependent variables in each cell. So over here in the rows are the dependent variables, the vote, voting for Democratic candidate, voting for Republican candidate. And on the columns are the independent variables, and this is having a Democratic partisan identification and having a Republican partisan identification. And then each cell is the frequency in the data of the combination. So we see here is 200 in the data in the sample we have. There are 233 cases of which a Democrat voted for a Democratic candidate, and 18 cases only in which a Democrat voted for a Republican candidate. Over here we have 43 cases in which a Republican voted for a Democratic candidate, and 230 cases in which a Republican voted for a Republican candidate. No matter how many different categories you have in the dependent or the independent variable, you just make a table out of it. It could be 2 by 2, it could be 3 by 3, it could be 400 by 10. It doesn't matter, whatever number of categories you have in your data, that's how big your table has to be. Now this table does not require any stats. You can look at it and say, I guess partisan ID is pretty important for vote choice. That is a well-known fact in political science. But what happens if we had a much closer call that we couldn't just eyeball as being relevant, as we couldn't just take a look at and be sure we're right? Okay, here's a harder example. And these are kind of made up, so don't take the results of this as meaningful. The previous one was also made up, but it is true. Do people with college degrees vote differently from people without college degrees? This is a different example, and again, we have two different categories, the same two categories for the dependent variable, but our independent variable is no college degree and college degree. And again, we put the number of individuals in each of the cells. And we have 209 over here, so no college degree and vote for Democrat, and so on and so forth, with a different number in each one. If we were to figure out what percentage of each of the independent variables ended up with each dependent variable, we would get numbers that are pretty close. 55% of those with no college degree voted Democrat, and 59% of those with college degree voted for Democrat. So the question is there a difference here? Did more no college degrees vote Republican? It seems like, relatively speaking, a little bit did, but is that significant? Is that a real effect, or just due to random chance from our sample? Right? I would guess from looking at this that no, there's probably no difference, but the numbers are decently large. And the difference is not zero, right? It appears to be about 3-something%, right? 3.8% or so. So that might be close. That might be enough to make it significant. So we're going to go through this example and see if it is significant or not, and see, more importantly, how to go about figuring this out in general. Okay, so the way we do this is we start by making a hypothesis test, right? Start by setting up our hypotheses. And we're assuming the first step that we already assumed that we had a random sample. Okay, so hypothesis test. Our research hypothesis for any crosstab like this, for any case where we have two categorical variables, is that there's a relationship between the independent variable and the dependent variable. Here, we're going to assume there's a relationship in our research hypothesis. We're going to state there's a relationship between education and vote choice in U.S. congressional elections. This is not directional. I don't know if education leads to more or less choice, or choice in one direction or the other direction, but we can't really figure that out usually directly in these kind of crosstabs using a chi-squared test. We'll see how to kind of back that out, but it's not going to come out naturally necessarily. The null, as always, is there's no relationship between the independent and dependent variables. So here, there's no relationship between education and vote choice in U.S. congressional elections. If we reject the null hypothesis, then we say we are fairly certain there is some kind of relationship between the independent and dependent variables. That's the second step there. Now, the third step of our sequence of steps was to figure out the distribution, the sampling distribution. Now here, we're going to be looking at relationships in a table, so this tabular analysis, and we're going to have to use something called a chi-squared statistic and a chi-squared distribution. This is going to be a test, strictly speaking, of statistical independence. We're going to try to see if the values in one variable are independent of the values in another variable. This is a nice test. It's a non-parametric test in the sense that we're not going to calculate any particular thing. We're just going to be seeing if we're going to calculate a statistic, but we're not fitting a parameter within our model. So we're going to calculate some chi-squared statistic, which can be distributed according to chi-squared distribution. In practice, that means we look up from a different table and then see if the statistic we calculate will be big enough to reject the null hypothesis of no relationship between the independent and dependent variables, to reject the null hypothesis of no association. Okay. Again, here our goal is to determine if there's a systematic relationship between our independent variable of education and our dependent variable of vote choice. So the way to do this, and this harkens back to our discussion of probability, the way to do this is to figure out what we would have expected to have seen had there been no relationship. So we're going to produce the table that we would have expected to have seen if the x and the y variables were completely independent of each other and unrelated. So again, what we're going to do is we're going to figure out what we would have seen had there been no relationship, no correlation between our x and our y. If it turns out that our table that we did see is very, very different from the table that we would have expected to have seen given no relationship, we're going to reject the null hypothesis. If, however, the table we did get is very close to the table that we would have expected to have gotten given the null being true, given no relationship, then we do not reject the null hypothesis. The larger the difference, the more likely we reject the null. That's it. And the chi-squared is going to be a measure of how different our table is from the table that we got. Sorry, how different our table is that we got from the table we would have expected to have gotten given no relationship. How does that work? It's actually pretty straightforward methodologically. First, you calculate what are called the marginals in the table. These are the totals of each row and each column. So here's our table. We total the rows, we total the columns, and we total the total. And it's a good check. Each row gets totaled over here. These are row marginals. Each column gets totaled down here. These are column marginals. And then these both have to add independently to the total number of data points you have, n, which is 759. If they're different, you made an addition mistake somewhere. Okay. Now, once we have these marginals, these row and column totals, we're going to use the marginal totals to calculate the table we would have observed had there been no relationship between the variables. Right? And we do that because we already know now how many Democratic votes we have, how many Republican votes we have, how many people had college degrees, and how many people didn't have college degrees. If there is no relationship between the two variables, then the proportion of individuals with college degrees should be split. Then all the individuals with college degrees should be split proportionally between Democratic and Republican voters. Right? So if 1/3 of all my voters had college degrees, then we should split them, between Democratic and Republican voters without regard to anything else. And if 2/3 had non-college degrees, then we split them as well. We split them up based on the total number of individuals who are Republican and Democratic voters in our sample. So how does that work exactly? Let's say it again a different way before I go on, because if there had been no relationship, the probability of someone without a degree voting for the Democrat would be the same as someone with a degree voting for the Democrat, and so on, right? That's another way of saying it, maybe a little clearer than I just did. Right? So in other words, there should be no effect of your college degree or not on how you vote. So how do we do that? Okay, well, we're going to multiply the marginals for each cell and divide by the total number of observations. So to figure out what the expected number in this cell is, we multiply 434 times 378 and then divide by 759. Now, why is that? Well, if you look at this, this fraction is the fraction of individuals in the sample who voted for the Democratic candidate. Then, if there are a total of 378 individuals who have no degree, then the proportion of the no degree people who should vote for the Democratic candidate should equal the proportion of them overall in the population, overall in the sample who voted for the Democratic candidate, regardless of whether or not they have a degree. Let me say that again. 434 over 759 is the proportion of the Democratic voters in the sample. If it doesn't matter if you have a degree or not in terms of how you vote, then each type of degree, each type of voter given their degree, should be split up according to the proportion of individuals who voted for the Democratic candidate and the Republican candidate in the population as a whole, independently of the degree. So, there were 434 over 759 individuals who had who voted for the Democratic candidate overall. There are 325 over 759 who voted for the Republican candidate overall. We're going to split them up according to that proportion within the no degree category. Then we'll do the same thing with the degree category. Again, there are 434 over 759 individuals who voted for the Democratic candidate. That's where this comes from. And there are 381 people who have a degree. So that's where this comes from. So we split the 381 up proportionally between Democrat and Republican voters according to the total proportion in the population. If you don't want to think about it this way, the other way works as well. The proportion of overall individuals who have a degree is 381 over 759. So we're going to split all the Republican voters up, the 325 Republican voters up, with those among those with degrees, according to the proportion who have degrees. And over here, the other ones, the other individuals get split up among the proportion of who don't have degrees. In this case, they're pretty similar, but that's how you'd also do this. And you go through and you work this out, and what you see is because the number of individuals with degrees and without degrees is very similar in this sample, we would expect very similar numbers between each column. In contrast, the sample as a whole has just more Democratic voters, right, about 33% more Democratic voters, so we expect to see more Democratic voters of each type in our expected table. So what we're really doing here is we're taking into account the fact that we should not expect to see a table with equal numbers in all four cells because we don't have equal populations of all four categories. We have more Democratic voters by chance in this sample, and therefore we should expect to see more Democratic voters in an expected table. Okay. The degree part, though, the degree comparison, is pretty equal because we expect to see roughly the same number of individuals over here as over here in each column because the number of individuals who have degrees and don't have degrees is very similar in our sample. If this number were twice as big, then the numbers in this column will be twice as big as the numbers in this column. Okay. So, and we go through and we can do a percentage on this, and what we see is, as expected, there's more people who are Democratic voters than Republican voters in this sample, and roughly equal numbers who have degrees and not degrees. So this is our expected table. Okay. So now that we have an expected table, we have to compare it to our observed table. by doing that, we can then calculate our chi-square statistic and make our comparisons that we need. We're going to do this comparison cell by cell. So we have 4 cells in our table. Within each cell, we're going to take the observed value, the one we actually got, and subtract from the expected value. Now we don't want negatives here, so we're going to square that difference. And then we're going to divide that difference by the expected value. And I'll show you the next table so you can see that written out in math, but we're going to take the difference between the observed and expected cell, square it, divide by the expected cell, and put that in that cell in our calculation of the chi-squared term. And then we're going to add those all up. So in this case, we're going to add 4 of those up for 4 cells, and that would be our chi-squared statistic. So how does that work? Okay, so here's our observed table we had. Here's our calculated expected table. We subtract expected from observed. We square it. We divide by expected. We get 0.24. Same thing over here, 0.23. And then down here as well, right? So 169 minus 161.86 squared divided by 161.86. And that gives us the whole table. Now we have 4 different values that we're going to add together to get a chi-squared. So we add them together and we get a chi-squared of 1.098. That is our test statistic. Our question then is that big enough to reject the null hypothesis or not? How do we figure that out? Well, for normal distribution, the critical values we discussed, and we'll discuss again later in this next module, was about 2, 1.96. If we were bigger than 1.96, we said we could reject the null hypothesis because we were more than 2 standard deviations away from the expected mean of 0. It's a different distribution here. It's a chi-square distribution. It looks different. It starts at 0 and goes out to infinity. The way you compute the critical value is as in this slide. First, you calculate degrees of freedom. So those are coming back again from before. The degrees of freedom in this calculation are the number of columns minus 1 times the number of rows minus 1. In this case, we have 2 rows and 2 columns. So it's 1 times 1, or just 1 single degree of freedom. Then we find a table of chi-squared probabilities. This course, in the live version of this course, uses the Kelstedt and Witten book. And this is Appendix A in that book. You can find these tables online as well pretty easily. You just look for chi-squared tables, and you can find them pretty easily. You find the degrees of freedom over here in the rows. You read across. The probabilities are the p-values you want to use. 0.05 we discussed was the p-value we want to use for a cutoff for 95% confidence. So we look at this column here for 0.05, and you see here helpfully it says non-significant for this stuff, but significant for this stuff at that 95% confidence level. And we read over from 1, so the first row is 3.84, and if we want it to be 95% confident that our independent variable was associated with our dependent variable significantly, we would need the chi-squared statistic to be greater than 3.84. Is it? No. It's about a third of 3.84. It's less than a third of 3.84, so it is not significant. It's not significant even at the 90% level. Right? It is simply not significant. So because the chi-squared statistic we have is smaller than its critical value, we cannot reject the null hypothesis in this example. Therefore, we cannot state that there's a relationship between having a college degree and how one voted in the 2006 congressional election. Okay. That's how this works. Again, if it's useful to go back, you can go back and look at the example again. I'm going to move forward here to do a different example with 3 rows to show you what's different and what's not different when you have more rows and more columns. There's 3 rows and 3 columns. So this question is the 2000 National Election Survey asked respondents if national security had gotten better or worse since President Clinton took office in '93. And here again you see a pattern. So we can check out if this pattern is due to random chance or if it showcases an actual difference by independent variable, which here is partisanship. So here we have 3 options in the dependent variable. There are 3 different answers to that question: worse, the same, or better. and this is an ordinal variable, right? The question is, has it gotten better or worse? If worse is on the sort of lowest end of the scale, it goes worse, same, better. We have a nominal variable over here on the independent variable side. We have Democrats, Independents, and Republicans. And then each of these cells tells you the frequency of among the respondents of people with combinations that have say worse and are Democrats and so on. Okay. So how do we do this? Well, the first step is to calculate the marginals. So we add up each row and each column to get the marginal values for each row and each column, and then add them all up to get the total number of data in the data. Here it's 1,600 or so. Now we calculate the expected table, right? The table we would have expected to have seen if there had been no relationship at all between the independent variable of partisanship, partisan ID, and the dependent variable of answers to that question about national security improvements. And in each case, all we did is take the marginal for that row, multiply by the marginal for the column, and divide by the total number of data points. That's what we do in every single cell in this table, and we calculate that, we get these numbers. This is our expected table given the hypothesis of no relationship between dependent and independent variables. Once we have that, we calculate a chi-squared test statistic. So we take the observed value, subtract from that the expected value, square it, and divide by the expected value. We do that for every single cell. So as before we had 4 cells, now we have 9 cells. So the number of things to do is obviously much greater in terms of calculations, but in terms of the logic and the theory, what we're talking about, nothing has changed at all. And from that we get our chi-squared table. We can already see the numbers are big, so we're going to guess what's going to happen here, but let's work it out. We add up for every single cell all these numbers. So we get a total chi-squared, when you do this, of 164.3. Now I figure out the degrees of freedom. Well, we have 3 rows and 3 columns. Degrees of freedom are 3 minus 1 times 3 minus 1, which equals 4. So in our table, we're going to find the 4th row of our table for 4 degrees of freedom. We're going to read over to the 0.05, so a 95% confidence level, and we're going to read off our critical value. Here the critical value is 9.49. Now 164.3 is much greater than 9.49, so we can safely reject the null hypothesis. Because of that, we can say that the 2 variables are not independent. With 95% confidence, actually much more than 95% confidence, we can say there's a relationship between partisanship and opinion on that question. Right? And in fact, you can see if you read over here, even 99%, we're well in advance of that, well over that. So we can say with high confidence that there's a relationship between partisanship and answers to that national security question. Okay, so that's what you get out of the chi-squared. There are limitations of it. We can't tell from the chi-squared by itself how to describe the direction or the size of the relationship. Right? All we get is, because we're squaring everything, right, we're not going to know what direction differences are. And the chi-squared itself just tells you how far the relationship is from expected, but you don't know if it's because of one cell or many cells, so it's difficult to figure out assess the size of the relationship that you see. And particularly with more than 2 columns and more than 2 rows, you can't parse out where the differences come from, right? Are independents different from Democrats and the Republicans? You're getting a holistic view of that it does matter what category you are in the independent variable in terms of what your answer was in the dependent variable, but you're not parsing out where the differences come from and if there are differences between any pair of those independent variable categories. Also, just having a big sample size is going to give you a more significant relationship, but that might not be very substantively important. One thing you can do is to go through and let me skip back here, do what we did back here, which is to compare the percentages we would have expected to the percentages we actually got over here. And here we're not seeing highly different percentages, but if you had a strongly significant relationship, you might see very substantially different percentages. Like over here, right, there are 240 in this column and 270 in this column, and almost all of them are on the diagonal. So we're seeing very different percentages, and these percentages can give you a sense of what the direction of the effects are and how big the effects are. But importantly, the chi-squared by itself is not going to do that. The chi-squared just tells you whether or not the association between the two variables is significant, whether or not they're independent or not. So whether they're independent or not. If the chi-squared is bigger than its critical value, we say you can reject the hypothesis that they're independent. And that's it. This is the first example of hypothesis testing that you're seeing here for categorical variables. Next time, we're going to move on to continuous variables.